has had a really profound influence on my scientific career. And he has also played a very important role model for our community, and so I'd like to thank him really warmly for that. So today I'm going to discuss one instance where non-Archimedean techniques or non-Archimedean geometry can say something about complex geometry, and more precisely about degenerating family of holomorphic objects. So this is definitely not a new idea. But I'd like to apply it in the context of holomorphic dynamical systems, following the seminal work of Morgan and Shalon in the 80s, where they built compactification of the family of representations of a fixed finitely generated group in SL2 by adding some representation over a non-Archimedean extension of C, and also of the more recent work by Laura Demarco and Yan Kiwi. Okay, so before stating my main result, I'd like to recall a few basic facts on the dynamics of complex endomorphism of the projective space. And so let me start by taking such an object, a holomorphic map from pk to itself, where k is greater or equal to 1. So the case where k is equal to 1, so the case of a Riemann sphere is already very interesting here. And so such a map is given in homogeneous coordinates by k plus 1 polynomials to pk, where the pi's are homogeneous of some degree, let's say d, which I will always assume to be greater or equal to 2. And the fact that f is a holomorphic maps can be translated into the condition that the common zeros of all these polynomials in ck plus 1 is reduced to the origin. Okay, so studying the dynamics amounts to look at the iterates of this map, which I will denote by f to the power n. And usually you're interested in, so you pick a point in pk and you look at the orbits. So the set of fn of x, where n tends to infinity, and you try to describe what this sequence does on pk. So you have to understand that, for such a map, usually, such a map exhibits some chaos. So you have sensitivity to initial conditions, meaning that on some part of the physical space on pk, if you follow one orbit and you perturb a little bit this point, this original point x, then after a finite number of iterates, then these 2 points become very, very far one from the other. So keeping this in mind, it's very hard to describe completely this of orbit, and so one tries to construct invariant objects, so mainly invariant measures. Invariant measure by our dynamical systems f, and use this invariant measure to give some stochastic properties of our dynamical system. So let me recall how Fornes and Sibony used pluripotential theory to construct interesting invariant measure, an invariant measure that captures somehow the most chaotic part of this dynamical system. Okay, so first, before constructing an invariant measure, you construct a positive closed 1-1 current, which is invariant. So let's take the Febini study form, a 1-1 form on pk, and pull it back by our endomorphism f. Then this is homologous to d times this Febini study form, and so it can be written that omega f plus dc of some smooth function, which can be written here completely explicitly as the log of the sum of the square divided by sum of the zi square to the power d and maybe there is 1 over 2d. Okay, so now you can iterate this equation. So let me denote this function by phi of f. So iterating this equation, so if you pull it back by fn, you get a sequence of smooth 1-1 forms. So plus a DDC of some series here. So sum from j equal to 0 to n minus 1, 1 over d to the j, phi f composed with f to the j. And the other observation here is that this series actually converges uniformly to a continuous function. Let me call it g of f, so which is continuous on pk. So which amounts to say that this series, this sequence of a smooth 1-1 form converges to a positive closed 1-1 current that is called the green current, T of f. Okay, so this positive closed 1-1 current is invariant under the dynamics. When you pull it back by f, you get d times itself. And locally, it has a continuous potential, so you can use Bedford-Taylor theory and to construct an infinite measure. So you can look at mu of f, which is the case exterior power of T of f, and this is a probability measure, which is invariant under the dynamics even more. It's ergodic. And one can show that it captures the most chaotic part of the dynamics, so meaning that it has, so it is, one can show that it is the unique measure of maximal entropy. So since the entropy will not play a key role in my talk, I'm not going to define this. Just keep in mind that this is an important measure where the dynamics is as chaotic as you can imagine. Okay, so now on the support of the measure, you can you have a sensitivity to initial conditions, and to measure a little bit how fast points escape from one to the other, you introduce the notion of Lyapunov exponents. Which is a way, so it's a non-negative real number. Let me denote this by Lyapunov of f. And if you want, it measure the infinitesimal expansion of your map f along a generic orbit with respect to mu of f. So more specifically, so here I'm going to be interested in the sum of the Lyapunov exponent, and so I will consider the local volume expansion of f along a generic orbit, and so by definition this number is the integral of the following function. Respect to the invariant measure mu of f. So you look at the differential, you have a metric induced by the Fermi-Distany metric. You can compute its determinant, take its norm, and take the logarithm. So it's a bounded function which is equal to minus infinity on the ramification locus of f. But since mu of f is local, it's the Mongean pair of a continuous function, then it integrates any logarithm of modulus of a holomorphic function. So this number is well defined. It's finite. And by Birkhoff, for almost every point with respect to this measure, then this is equal to the limit 1 over n as n tends to infinity, or 1 over n of the log of the determinant of the nth, the differential of nth iterate of f evaluated at this point x. Okay, so this number really computes the local volume expansion of the differential along a general orbit, a generic orbit. So the first, so I claim that this number is non-negative. So this is actually a theorem. Which is due to Briand-Duval. So the theorem of Briand-Duval says that for generic points on the support of the measure with respect to this measure mu f, then the differential is expanding in all directions. And so as a consequence of the results, one obtains a lower bound for the Lyapunov exponents. The Lyapunov exponent of f is at least k over 2 times the logarithm of a degree. So which is a positive number. Okay? So at this point, I'd like to mention another beautiful theorem by Christophe Dupont, which characterize those maps for which you have equality here. Okay, so when the Lyapunov exponent is as small as you can imagine, so Lyapunov of f is equal to k over 2 log d, only if f can be lifted to an endomorphism of an abelian variety of a complex story. So this is a very, somehow a very extremely rigid situation. Okay, so now so this is what I want to say about the dynamics of one endomorphism. So now let's take a family of endomorphism, more precisely a meromorphic family of endomorphism parameterized by the unit disk. Ft now is as before, so determined by k plus 1 homogeneous polynomials of the same degree d. So T is a complex number in the unit disk, and the Pi are polynomials in k plus 1 variable, but now the coefficient varies in T holomorphically on the punctured disk with, say, possibly one pole at 0. Okay, so this is the ring of holomorphic function or meromorphic function on the disk with at most one pole at 0. So you can think there are many examples of such a thing, but you can just think of Ft of z as being, for instance, the quadratic family, which is z squared plus 1 over t. Or in a higher dimension, you can also make endomorphism degenerate to automorphism. So one way of doing this is, well, you start with the here. So you start with a Henon automorphism. So this is an automorphism of the affine plane, and then you perturb it to a family of endomorphism, global endomorphism of P2. I have many more examples. Okay, so once you have such a family, then you can look at these measures of maximal entropy, mu ft. And so let me recall that this was defined as the limit 1 over d to, so this will be the Monge-Ampere, or if you want the k-wedge product of something. So d 1 over d to the n. And here was the Fermianist uniform plus the ddc of some explicit functions, the sum of the pi t to the square, or di to the square to the power d. And so this converges to what I denoted by the green function of ft. And the observation here is that at least when t belongs to, so this is well-defined if t is non-zero. And as t is not equal to 0, then in fact you can observe that this function here is actually continuous in 2 variables. So this green function defines a continuous function from pk cross d star, which implies in particular that this family of probability measures behaves in a continuous way. Now, using a little bit of pluripotential theory and say Chan-Levin-Nirenberg's inequalities, then you can also show that the Lyapunov, so first observation is, so this sequence of measures is continuous, at least when t is non-zero. So when t equal to 0, a priori you degenerate, and so you don't exactly know what can happen to this measure. It could converge to some atomic measures or to some measure that you don't really control. And so what I claim is that, in fact, the Lyapunov exponent, which is this integral, is also continuous. So in fact, there is more. So if you argue a little bit more, what you get, so this is a theorem by, say, Dean and Sibony. So not only this function of Lyapunov exponent is continuous, but actually it's a Holder continuous, and it's also subharmonic. So which reflects the fact that somehow here you're taking the logarithm of modulus of something which is holomorphic in both variables z and t. So here's Holder continuous and subharmonic. On the puncture disk. Okay, so one observation here is that for someone working in dynamic system, this statement is quite surprising. The fact that the measure is continuous. So the measure is a locus where the dynamics is as chaotic as possible. And somehow what is claimed here is that when you move the parameter, then locus does not change too much, but you have to be careful. This is not true for the support of the measure. So be careful that when you look at the map T goes to the support of the measure. So it's a map from the punctured disk to the set of compact subset of pk, which can be endowed with a metric. And so this is not continuous. In general. So here, this is a weak topology of measures. Okay? So what's happening is that you have points where the dynamics change actually quite drastically, and then you see, at least in dimension 1, this is completely understood. In higher dimension is much more complicated to analyze, but where you see the support explode or reduce, so this kind of thing. So sometimes you can have, for some t, the support can be a counter set, and then suddenly it goes through some bifurcations, and then it becomes connected, or with positive Lebesgue measures. Okay? So this is somehow kind of surprising. This second remark here, so I'm not going to emphasize too much, but the second remark is that, so when you look at the Lyapunov exponents, and since you know that it's subharmonic, it's natural to look at the measure, which is the Laplacian of this function, and the DDC of this function. And the support, so now it lives on this set of parameters on D, or on D star. And this measure, so the support of the measure somehow captures the locus where the dynamics is unstable. So that's a measure characterize the locus where the dynamics is unstable. So it's not exactly the locus where the support of the measure is not continuous, but almost. Okay, so let me state now this main result, at least a simplified form of this of my main result. So as before, so Ft, so family of endomorphism of pk, so parameterized by the unit disk of degree d at least 2 with possibly a pole at 0. And so now you can look at this Lyapunov exponent, the Lyapunov function. So we know it behaves very well outside the puncture. And then the claim is that when you get close to the puncture, then the Lyapunov exponent explodes like a constant times the log of t. So there exists, so for some non-negative lambda.
What do you mean by pole at 0?
Sorry?
What do you mean by pole at 0?
Sorry? I don't.
What do you mean by pole at 0?
So it's a meromorphic, so it's a holomorphic analytic family outside 0, and it's meromorphic at 0. So if you write this way, so this means that the PIT equal to 0 if t is non-zero. Okay? Okay. So let me call this E of t. So it's a function which is somehow the error terms between this very simple behavior and the function Lyapunov of ft. And so it's quite interesting to try to control this error function, and very little is known about it. So in general, E of t is not bounded, it's unbounded. So this is an example by Demarco and Yusuke Okuyama. And but under some circumstances, this error term is actually continuous. So it's continuous well when ft is a family of polynomials in one variable. So I understand that this seems quite a very, very strong assumption, and but just recall that already for the family of quadratic polynomials, there are some big open problems that probably deserve Field's medal. So I mean, this setting is already very interesting from the dynamical point of view. No, it's possibly there is a pole. But of course, it's not very interesting if you have no pole at 0. Okay, well, okay, I'm not very clear about what a pole is. Okay. So the pi here are meromorphic. Okay, but like you can, since this is given homogeneous coordinate, you can always multiply by t to a huge power, and then all polynomials become actually holomorphic. Okay. What I claim is the important point is that for t non-zero, these are really endomorphism of pk. When t equal to 0, then something else appears. So keep in mind these two examples. Okay. So maybe here, so the picture is as follows. So we have here is P1 cross unit disk. You have the line infinity, the set of points at infinity here. For t non-zero, you have quadratic polynomials, okay? And for the fiber, t equal to 0 is actually mapped to 1 point at infinity. And when you look at the induced map on P1 cross D, this point there is a point of indeterminacy. Okay, so this is a geometric picture somehow. Here it's a little bit different. Okay, so let me give actually a proof of this result. And then the next step will be to interpret this constant lambda in, as a non-Archimedean quantity, more precisely as a Lyapunov exponent of some natural non-Archimedean dynamics induced by this family of endomorphism. Yeah, okay. So you want to understand the following quantity. So the log of determinant of the differential respect to the invariant measure ft. And since the invariant measure is defined as a limit of smooth forms, in fact, you reduce to understand the following type of integrals. Then omega plus the DDC of the sum so here this is a pullback by f, say by fn. So d to the n, and then maybe 1 over 2 d to the n. So you want to understand such a thing. And here the point that this log of this norm looks exactly like this kind of integral. So it looks like log the norm of homogeneous polynomials of some degree, depending on the with coefficient that are meromorphic function on t, divided by some. So let me call it q of t, sum of the square, to the right power, say delta. Okay, so this is a homogeneous polynomial of degree delta with, again, with coefficients that are meromorphic with a pole, possible pole at 0. Okay, so this is quite explicit. And the key observation is that, so things can go wrong when you work over, so if you work over pk across the unit disk, so this function can behave quite bad. But if you blow up the central fiber in the right way, then so this family of polynomials gives you a family of section of the right line bundle of the pullback of O of d to the n on the product space here, and so it has some kind of base locus, so which is current sheaf of ideal. So if you blow this base locus, then you obtain a nice model where this function behaves very nicely. And so what you get is that you can construct a model X where, in fact, this current will decompose as, so let me not write this again. So decompose as a smooth current plus some vertical divisor. And now when you look at this integral, so you can forget about this divisor. You have here a smooth form. And this function here, well, when you get close to the central fiber, is basically you can estimate directly as constant times the log of the distance to central fiber. And if you put all this information together, then in the end you get exactly this main result. Okay, so let me explain now how you can give a non-Archimedean interpretation of this number lambda. And so let me explain how to attach non-Archimedean dynamical systems to my family f of t. So this is completely elementary. So recall that my polynomials there, pi of t, they are polynomials with coefficient in some ring. And the idea is to endow this ring with the t-adic norm. You have an element in here. It's you can expand it as t to the j times a naught plus sum of al tl. A naught on 0, and the t-adic norm is just e to the minus j. Okay? So if you look, so usually one prefers to take the completion of, not to work with a ring, but to work with complete rings. And if you take the completion of this, well, you get the field of Lorentz series with the t-adic norm. And so now by viewing these polynomials as elements in the field of Lorentz series, which is t-adic, well, you get a dynamical system that I will denote by capital F, which is, again, an endomorphism of pk, but now over the field of Lorentz series. And this is an endomorphism of degree d. So now I'm going to explain that, well, one can define the Lyapunov exponent of this endomorphism, and this constant lambda is actually the Lyapunov exponent of this capital F here. Okay, so the constant, an invariant measure. And so basically, I need to make sense in the non-Archimedean context of this, well, this quantities of a pullback of the study form by the nth iterate of f. And so one way of doing this is to work on line bundles. So the observation. So if you write this equation here, this can be interpreted by saying that you have a metric. So let's say, let's pull it back by the nth iterate. And so you can interpret this as follows, where there is a metric. Let me denote by norm index n on, so this is a metric on O of 1 over pk, which is defined as follows. So a section is just a linear polynomial. And you take the norm of L divided by this quantity here, subtly normalized. And if you take the curvature of this metric, well, you get exactly this 1-1 form. So C1 with this metric, exactly this 1-1 form. So even though we're not, it's quite hard to make sense out of what a smooth 1-1 form is over a non-Archimedean field, one can define in the same way the notion of metrics. And so, and here, you define the metric by setting, by taking exactly the same formula, except that here you're now over the non-Archimedean field, so you better replace the sum by the max. So then you have a theorem of Zhang, which is in fact amounts to exactly the same computation as in the beginning, is that this sequence of metrics converge to a continuous, so semi-positive metric on O of 1. And then you can use the theory of Chamberlois that attach to any such metric of volume form. So in fact here a probability measure. So the say curvature, one can define the curvature volume form of this continuous semi-positive measure. Now what is this object? It is a probability measure. Let's call it mu capital F on, well, the Berkovich analytification of my space, which is a compact, a nice compact rectangular space. Okay, so once we have this measure, so one can show this measure is also invariant by capital F. And there is an argument by Thuillier and Chamberlois that says that exactly as in the complex case, this measure integrates all logarithm of a norm of a holomorphic function. And so you can make sense of log of the determinant of the norm determinant of the differential with this. And well, this is a finite number. Okay, so now the claim is that this constant lambda upstairs is in fact the Lyapunov exponent of a dynamical system capital F. And how does the proof goes? Well, you look at the proof here, and then you have to unwind. So you get some formula actually for the constant lambda, and you unwind the definition. And in the end, you remark that well, this constant lambda is exactly the same integral as was defined by Thuillier and Chamberlois. So let me go a little bit further in the last 10 minutes and explain how, in fact, the proof of this statement gives you some continuity statement for the family of measure mu t, but in a space that mixes both complex analytic parts and a non-Archimedean part. So what I'd like to state is that you have, so the assumptions are exactly the same. So meromorphic family of endomorphisms of degree d. So you can look at these measures mu of t when t is non-zero. And then this converges to the measure mu capital F. Okay, so this statement looks a little bit strange because this measure lives in pk cross t, and this measure here lives on the Berkovich analytification over the field of Laurent series. And so to make sense out of this statement, well, one needs somehow to construct a space that contains these two kind of objects. And this was done by Sébastien Boxon and Matthias Jonsson, based on an idea by Berkovich that they call the hybrid space. So that does exactly the job. So let me state this as a theorem. So there exists a compact space. So let's call it the hybrid space attached to pk with the following properties. So together with the continuous surjective map from to the closed disk of radius 1 over e. So P is proper, continuous, surjective. And so what I'm going to explain, that's the fiber, the preimage of 0 is homomorphic to the Berkovich identification over the field of Lorentz series. And the preimage of the punctured closed disk is homomorphic to pk cross the punctured disk. Okay, so together with two homeomorphisms. Let's call it psi NA for non-Jacobian. So that goes from the Berkovich identification over the field of Lorentz series of pk to the fiber of this map P over 0, and another homomorphism psi from pk, so from the standard pk over the complex numbers, cross the punctured disk to the preimage by P of the corresponding object here, so punctured disk. And here, so here you have two projections. You have the first projection, and here you have the map P. So it goes down to the same disk, and this diagram here is commutative. Okay, so what is the picture or the image? So you start with the pk across the disk. Then you remove the central fiber, and you replace the central fiber by this Berkovich analytic space. Okay, so when k is equal to 1, this Berkovich analytic space is basically a tree, and so a very hairy tree. Non-metrizable. So you get some object like this. And so the statement here, in fact, is that, so these measures live in that space here. So you can push it by psi. So this is now in the hybrid space, and this converges to the corresponding image under this homomorphism of the measure mu capital F. Okay? And the proof goes as follows. You look at the proof I didn't really explain here. But then you see that if you translated this, then you get exactly that this result. So let me just give a flavor on how to construct this hybrid space. Maybe not for pk, but for the affine space. And so to motivate the definition of this hybrid space, let me recall what is the analytification, the Berkovich analytification of the affine space of dimension k. So as a set, as a topological space. So this is a set multiplicative. So this is some kind of spectrum on the ring of a regular function on this space. So this is a multiplicative set of multiplicative semi-norms on the ring of a regular function here. So of C of t bracket W1 Wk. And you look at multiplicative semi-norms. The restriction to the base field is a t-adic norm. So you can handle this set with the topology of the pointwise convergence, and in the end you get a locally compact space that is retractable thanks to a theorem of Berkovich. So now let me observe that, in fact, the analytification of the affine space dimension k over C can be defined exactly in the same way as a topological space. So this is a set of multiplicative semi-norms on C, W1, Wk, whose restriction to C is the standard Euclidean norm. So this is supposedly W1. And so this gives you an idea on how to define this hybrid space attached to AK, where you look at a set of multiplicative semi-norms now on, well, the ring of a holomorphic function on a meromorphic function D with a polar T, bracket W1, Wk. So whose restrictions somehow are bounded by a norm which mixes the t-adic norms and the Euclidean norm. So bounded. So whose restriction to this ring is bounded by the hybrid norm. So what is the hybrid norm? So let me write. So A infinity, this is a standard Euclidean norm, and A naught is the trivial, so which is equal to 1 if A is only 0, and 0 if A is equal to 0. So this is for A complex number. And so what is the hybrid norm of a series like this? So this is a Lorentz series. So this is a sum of over all A of the max of the trivial norm and the Euclidean norm of the coefficients times e to the minus j. Okay? And so that was the last word. So what is this map P? Well, the map P from the hybrid affine space of dimension k to the unit disk is just the restriction map. So P is the restriction map. So you take a semi-norm on this huge ring, set it to the ring of meromorphic function at 0. Okay? And so then you have to check that the space of some multiplicative semi-norms bounded on this ring bounded by the hybrid norm is in fact canonically homomorphic to the closed disk. And then the existence of these two homomorphisms are basically trivial. So it comes directly from the definitions. Okay? So I think I'll stop here.